So today we're going to talk about how to solve targets 5.01a and 5.02b. Let's read the problem. Sci-Fo's brother Sci-Fi is a rocket skier with a total mass of 35 kilograms and propelled by a rocket power. The rocket force is 280 newtons and the coefficient of friction between his skis and the snow is 0.1. We should first start by drawing a force diagram for Sci-Fi. So, we know that he's propelled forward by a rocket force, which would be an applied force. We know gravity is pulling him down. We know he has a normal force holding him up. And we know there's a friction because it says there's a coefficient of friction. So we have a force of friction slowing him down. So, let's fill in the force table that we know right now, what we know about the force table. It tells us that the rocket force is 280 newtons. So we know the applied force is a positive 280 newtons because it acts in the right direction. We know the horizontal component of the force of gravity is going to be 0 newtons. The horizontal component of the normal force is going to be 0 newtons. Force of friction we don't know, but we also know that there's no force of friction in the y direction. So there's going to be 0 newtons there. We also notice the applied force acts to the right and has no y component. So we're trying to figure out the force of gravity. Well, we know that the force of gravity can be found by the mass times g. In this case, g is going to be 9.8 newtons per kilogram. So the force of gravity is equal to 35 kilograms times 9.8 newtons per kilogram, which gives us a force of gravity of negative 343 newtons. We know it's negative because the force of gravity acts in the downward direction, which is our negative direction. So we can fill in our force of gravity component, which is going to be negative 343 newtons. Looking at our table, we know that there's no net force in the y direction because the skier is not going to be accelerating up or down. So because he's going to be traveling at a constant velocity in the y direction, the net force will be 0 newtons. Once we have that, we realize that the normal force is just going to be the opposite of gravity to balance the forces out. Now we can figure out the force of friction, which would complete our force table. Earlier this unit, and a little bit at the end of Unit 4, we found out that the force of friction is equal to the coefficient of friction, which in this case is kinetic because the object's sliding, times the normal force. We've already found the normal force to be 343 newtons. And we know that the coefficient of friction is 0.1 because it was given to us in the problem. So the force of friction is going to be 0.1 times 343. This tells us the force of friction would be 34.3 newtons. But because the force of friction acts to the left, this force would be negative. Now we can finish our force table. We know the force of friction is negative 34.3 newtons. So if we add the negative 34.3 newtons with our other x component of 280 newtons, we're going to get a net force of 245.7 newtons. That's our sigma F, or our net force. And it's going to be acting to the right. So now we have to remember, well, how can we figure out the solution to this problem? We want to know, what is Sci-Fi's acceleration? So we have to show our work and write any equations that we use to solve. Newton's second law, which we can recall, we found in our unbalanced forces lab, was A, being the acceleration, equals the net force over the mass. In this case, we know the net force is 245.7 newtons, and the mass is 35 kilograms. So 245.7 divided by 35 gives us an acceleration of 7.02 meters per second squared. So we found that our acceleration is 7.02 meters per second squared using Newton's second law and finding the forces as we did earlier in Unit 4 and in Unit 5. Now let's talk about how to solve target 5.02b. A 90 kilogram man standing still on the moon experiences a force due to the moon's gravity of 146 newtons. Another 90 kilogram man back on Earth travels in an elevator accelerating downwards at negative 8.5 meters per second squared. So first, we're eventually going to be answering the question, which man feels heavier and why? It's going to be a good idea for us to first draw a force diagram for each of these men. So looking for the man on the moon. We know he has a downward force of gravity, which I told you was 146 newtons. Because he's standing still, we know that the forces here must be balanced. And there must be an upward force caused by the moon's surface, the normal force, which would also be 146 newtons. So this would be negative because he's acting down. So the net force in this case is 0. Now let's draw a force diagram for the man on the elevator. This man is on Earth. So we know he has a force of gravity pulling him downwards because of the Earth's gravitational pull, which is going to be equal to his mass times 9.8. So his force of gravity in this situation is going to be a negative 882 newtons downwards. We know that he has to have an upwards force due to the normal force because he's standing in an elevator, but we're not quite sure what that is yet. We know that the forces here are unbalanced because he has an acceleration of 8.5 meters per second squared in the downward direction. So in order to figure out what the normal force must be, we should figure out what the net force is. We know that the net force, is equal to the mass times the acceleration. So in this situation, his net force is going to be 90 kilograms times negative 8.5 meters per second squared, which gives us an overall net force of 765 newtons in the negative direction. Because we know that the net force is also the sum of all the forces, it's going to be the normal force plus the force of gravity, because those are the only two forces acting on the man. We already found that the net force is negative 765 newtons. The normal force we're not sure about, and the force of gravity is negative 882 newtons. So if we do a little bit of math, we add 882 newtons to both sides. We found that the normal force has to be 117 newtons in the positive direction, which would be up. This would give us an overall net force downwards of negative 765 newtons. So now that we have this detailed information about the forces acting on the two men, we can start worrying about the solutions to the problems below. So if the man on the moon were standing on a scale, what force would the scale read? Based on our discussion on elevator physics, we know that the scale reads the normal force. So we need to look at what would the normal force tell us for the man on the moon. So the man on the moon has a normal force of 146 newtons. So the scale would read 146 newtons. But now the man in the elevator has a lesser normal force than he would if he were standing still because he's accelerating downwards. The normal force for the man in the elevator is 117 newtons. So the scale would read 117 newtons. So let's talk about the answer to this question here. Which man feels heavier? So now we talked about what causes us to feel the force of gravity. The force of gravity pulls us down, but essentially it's the ground pushing us back up that causes us to feel that weight. So which man feels heavier would be the man with the greater normal force. So the normal force is what causes us to feel heavy. So which man feels heavier? The man on the moon. Would feel heavier because he has a greater normal force than the man on Earth. So again, which man feels heavier? The man on the moon, because his normal force is greater than the man on Earth in the elevator.